Tenemos un quórum.
Hi.
Hola.
Hello. Hi, hi.
Vamos, gente. Yeah. While we're waiting, does anyone want to ask any questions?
Yes, I have a first question. About the last problem, set number 7. I think that is in question 1. When we needed to calculate the spectral index alpha of S, that it's related to the particle distribution index P, right?
Yes.
The relation that we check in class was 2 alpha, it's equal to P minus 1. But
Yeah.
uh,
Sometimes there's a difference of a minus sign. Which
yes,
I went into great detail about, and I don't necessarily always adopt the same nomenclature, so I don't guarantee that it's correct.
yes, because when we were studying Crab nebula, we use 1 means P.
Yeah.
We get I get imaginary values in Fe and Fk functions.
Well, actually, the Crab nebula, right? So I gave you the spectrum,
Mhm.
and in fact, it's pretty steep.
Okay.
Right? I don't remember exactly what it was, and we quoted it in class too, I think, but it does end up being pretty steep in the radio. Yeah, I mean, I remember the plot of it's in energy, new energy. Sorry, F what's in new F new, or in equivalently F, or energy times flux, and there you have to be a little bit careful about how you choose the spectral index.
Okay. Thank you.
But yeah, I mean, if you take two fluxes or two frequencies and you measure the flux, you're going to get a slope, and you understand the way that it should go. That's the key point, right?
Okay.
So there shouldn't. I mean, however you define alpha in terms of this frequency to this frequency, right? It will work out. Right? As long as you have the correct definition of alpha versus what you're actually measuring. Does that make sense, Roy?
Yes. Thank you.
Yeah. Okay. Looks like we are all here now. Any other questions about last class? Homeworks? I think we only have of order 6 classes left.
I have a question about the homework, about
Yes.
the first point in the A point. I was wondering if the question is about the specific energy density or the total energy density, because but this is like the question, because the energy density can be defined in terms of as a function of the frequency, or can be defined as a total energy density.
Yes, so you want I think you want the total because you want to use that. I mean, I guess you can kind of do it either way, but I would thinking mostly of the total, if I recall correctly. And so you want to compare that to, say, the energy density of the other two things that I ask in problem B, right? And so you need it over some frequency range, and you could choose the entire one. which would be from whatever, -6 to 8 log EV. So you would have to integrate it in parts or whatever, but yeah, you could show both of those. I think the key thing is you want the energy density and the range that will be relevant for the inverse Compton scattering later on.
Mhm.
And so there is a sort of sweet spot in terms of the frequency range, but it's not going to be. I don't think it'll be necessarily too important because of the energy range that I if you do the full integration versus a small portion of it with its on the relevant area, I don't think it will be that different. I haven't done the calculation. But just thinking about it in terms of again, the energy, F energy, so that quantity is going to peak in this sort of optical range.
Okay, thank you.
Okay, other questions? Okay. So we're going to finish up sort of talking about sort of general continuum processes today, and then we're going to dive into atomic and molecular properties, I think starting next lecture. And so, I guess one thing, the final thing that we kind of have to come back to is the fact that space isn't necessarily empty. And when we talk about the vacuum equations or electromagnetic waves propagating through a vacuum, we have to modify that when we talk about propagating through a medium, right? And the medium could be the ISM, it could be the atmosphere, it could be interplanetary, gas and dust, and the solar wind. All of those things, while they have a very low density, it's not completely zero and it's not completely a vacuum. And so having particles in the way affects things, right? And so one of the ways that, I guess the other way that it will affect things is in terms of dust extinction, which we will talk about sort of at the end of this class, or not, sorry, the end of the semester. And so the thing we want to talk about today is basically plasma effects. And so hopefully you have seen them a little bit before, or at least heard about them. We've talked about them in Astro PH a little bit. And so, the critical thing here is if this medium is at all ionized, which a portion of it reasonably is going to be. For instance, the ISM, there are different phases of the ISM, and so you have a molecular component, a neutral component, and an ionized component, which can be sort of warm or hot. And so that ionized component is particularly important because you can get interactions between the electromagnetic waves and the ionized particles, obviously. And so we want to understand what the influence of this plasma has on radiation. And so if we consider an ionized medium, we have the ions and the electrons, right? And so the ions are going to have a charge Z times E, and the electrons will each have a charge E, and there should be sort of order Z times Z number of electrons per one ion, something like that, right? So we have some overall balance in charge on very, very large scales. And so we can talk about something called the Debye length, which is the distance over which a charge of value Q would be shielded by ions in a various solution. So you have some sort of charge Q here, and you have a bunch of say electrons here or other ions here, and over some distance, that whole thing, the electric field will be considered nulled out, because you have a balance of different charges. And so effectively what this leads to is some range over which the Coulomb field no longer affects the outer scales, right? And so we can think about, you know, this sphere of radius LD is the Debye length, and basically approximately there's going to be equal number of charge minus Q that cancels out the plus Q here. And so if we consider this in a little bit more detail, we have, you know, we want to basically have Z times the number of electrons equals this number of ions to have sort of charge neutrality throughout. And if we have this, how does this actually take form? So we have Coulomb's law, which is the, you know, Laplacian of the potential here is going to be equal to the charge density. And this charge density, we can sort of write this out. One solution of this would be of this form. And so here we have, you know, we have the electrons and we have the ions, and they both have a somewhat, you know, a form like this, but then we have this extra component here because this is has all the charge concentrated. And so if we assume that they're in equilibrium, hopefully, and so the temperature of the ions and the electrons is more or less similar, then, you know, this will mean that these exponentials are typically be small. We can Taylor expand them, and then what happens is the first terms cancel out, and under at least the assumption of charge neutrality, and we end up that the Laplacian is just of this form. And so we have this sort of the combination here will be this our charge neutrality, and we can consider, you know, this is the sort of delta function form of the potential, and then we have our potential here, and we have some other factors, and we can kind of group these other factors into something which is considered the Debye length. And so the Debye length formally is this temperature component divided by the number density of the particles. And so typically for Z equals 1, then this simplifies to, you know, for hydrogen only cloud or plasma, this simplifies to something that looks like this. And we can notice that there's just spherical symmetry here. And so we can take the Laplacian to be just this, and then equate that with this thing. And one solution of this is if the potential goes as this form. So basically, we have two limits here. One is that it should have a form of this at r equals 0, and the other is that it should be 0 at infinity. And so this exponential here satisfies that. But the interesting part about this is, of course, this is related between the radius and the Debye length. And so what this suggests is that at large distances, this potential is reduced depending on what's in here, right? And what's in here is just the temperature of the system and the density. And so this is fine, right? We have some sort of statistical attraction of electrons and repulsion of ions. They shield the primary charge here. And the ions and electrons should shield equally. And then their contributions, they should depend on their particle speed as it relates to the mass through the temperature. But it's not dependent solely on the particle mass. And so if they're in equilibrium, this should be somewhat accounted for. If R is much greater than this, right, then the free charge potential ends up being modified. So it's not just 1 over R, but it has this exponential term, which cuts off. And so we can think about this situation. What do we actually need here for this to apply? And so this requires that we have enough particles inside this volume that we're treating, which is going to be a volume of order Debye length cubed for a statistical treatment. meaning that the number of particles inside this volume must be much greater than 1, right? So we have a statistical average here. And so the inverse of this quantity ends up being known as the plasma parameter. And so what this typically means is that this Debye length is proportional to the number density, or rather the regime over which we can kind of consider this assumption meaningful will go as sort of the cube root, 1 over the cube root of density. And so this, we can translate this if we have sort of an electrostatic energy per kT, this requires, so this requirement here can be translated into something like this. And so we have that the number density divided by the average energy per particle, that should go as this, or should be much less than 1. And so basically this is, in a statistical regime, this justifies the earlier Taylor expansion that we had. So we have an estimate of this Debye length. And so if we do 1 over the square root of this Debye length, this is equal to the number density divided by kT. And we can think of kT as being NV squared for the electron at least. And if we regroup this, we have these quantities, these constants and the number density of electrons. We can consider this to be something called the plasma frequency. And so the velocity here is the thermal velocity of electrons, and omega squared is this quantity here, which is known as the plasma frequency. And to get an idea of what the hell that means, we can think of the following. So let's take an example where we have electrons in a plasma which are displaced by some distance x from ions. And so you have some separation of the charge, and effectively this is a 2-plate capacitor, right? And so you can estimate the surface charge density of these, which is going to be of the order of the number density electrons, the charge of the electron, and the distance between them, right? And so this means you'll have an electric field which will look like this, which comes from just integrating this quantity here. And we can satisfy, if we have an electron which moves in this, moves between these 2 plates, the equation of motion would just be that we'd have some acceleration here, which would go as the electric field times the charge divided by the mass. And so we can plug this in. So plugging in sort of this and this, we have something which looks like this, and we can again recouple these, noting this definition, and kind of repackage this as the plasma frequency times the distance divided by the density. And so this is sort of what we would consider a natural oscillator frequency for the electron in this charge separation. The ions in this situation, because you're packing much more charge into and much more sort of mass there, typically they oscillate at a lower frequency or slower rate. And so generally we can consider them fixed, and then the electrons are the key thing that's sort of limiting this or giving us our plasma frequency. And so if we calculate this out numerically, this has a sort of relation that's about 6 times 10 to the 4 times the number density. And we could change this into a frequency, and this would be equivalent to a frequency of about 10 kilohertz rather, times the number density. And so for relatively high density environments, say, let's say 10 to the 6, taking the square root of that, that's 10 to the 3, we're talking about maybe 10 megahertz regime. So this is sort of measurable, but for lower densities like the ISM, it's pretty low. Okay, so what this means is we have larger frequency forces or disturbances. Generally, this will set up faster oscillations, but the fast oscillations will end up sort of what is I guess I rephrase this. So if we have larger frequency forces of disturbance, these are going to set up faster oscillations, and then the faster oscillations that will be set up to kind of counteract those in terms of this sort of limiting scenario of an oscillator frequency. And so generally speaking, here the charge separation occurs for disturbances which, if there are basically what it means is that, so for this Debye length, we see disturbances which are on that scale are smaller, but on larger scales we don't see anything because the charge separation cancels out. And so for disturbances on these larger scale sort of sizes, we would go into a sort of neutral fluid MHD regime. And so we'd have to calculate it in sort of a different manner altogether. But on this small sort of scale, we can kind of consider this to sort of work. Okay, any questions so far? No. Okay, you're all still waiting for the punchline. Okay, so Rubik and Lightman go into much more detail here and set this up in a more rigorous way. So they take the Maxwell's equations and basically they have the sort of propagation of light will go like following these equations, and typically we can have that these variations are going to go as a function of e to the I times k dot r minus omega t, right, which is one of the solutions. And so we can assume here that the electron have a density n, and we have an isotropic plasma. For the moment, we're not going to consider any magnetic field, so we're going to just remove that. So this is 0, and we can simplify these equations quite a bit. And so we can have, then applying Newton's law, that the acceleration here, the force, is going to be given by the Coulomb field. And so if we then think about this in terms of oscillating quantities, we have a velocity associated with this acceleration, and this velocity will be proportional to this charge in electric field. And then we have this frequency of oscillation. And of course, it's a complex oscillation. So we can think about this macroscopic scale in terms of a charge density, right? And so the charge density is going to be the number of particles times the charge times this velocity. And we can interrelate this charge density to the field by this conductivity, where the conductivity is this set of quantities here. So we have our density, we have our charge squared, we have an imaginary component, we have our frequency and our mass again. And so if we assume that there's a charge conservation here, then this should hold. So the density of charge and the charge density, the charge density and then the current density, this is current density, not charge density. These things should equal out over some scale. And so repackaging, moving this on the other side and solving this for the charge density, we get that it's proportional to this sort of wave number times the current density divided by the frequency. And we can substitute in this thing here and get this and move out the conductivity here. And so we can repackage this in terms of a dielectric constant. And so the dielectric constant, we can kind of define the dielectric constant using these equations up here, and this here, we can kind of define this as 1 minus the conductivity divided by this frequency and an imaginary number. And so if we plug in our values for the conductivity here, we can end up with this dielectric constant is related to the frequency, the plasma frequency divided by the frequency squared. And so this extra dielectric constant will be plugged back into here when we are not in a vacuum. And so we can rewrite Maxwell's equations as this, right? So we just popped the dielectric constant in here, and we popped it in here, and otherwise we have something which appears fine, and the equations are source-free again. And so this can be solved before, as we would have done in a vacuum. The only difference here is that now we have this relation as opposed to just without this. And so we can think about this dispersion relation as this frequency, this frequency we're related to the plasma frequency and our wave number times the speed of light. Or the wave number is proportional to the 1 over the speed of light times this proportion. And so what's interesting here is that we have a bit of a problem in that if the frequency is below the plasma frequency, this thing is negative and the wave number is now imaginary. And so it doesn't propagate. If we plug this back in, what this ends up meaning is that, so we have this is imaginary and this times the imaginary number is now a real thing. And so we get something which decays on length scales, which are proportional to this quantity. So they're proportional to the 1 over the plasma frequency. And so what this really means is that we have a plasma cutoff frequency where we don't get any electromagnetic propagation. And so what happens in this case is rather than it propagating, it reflects. And so if we're talking about photons which are going through some non-vacuum medium, right, and then that medium has a plasma frequency which is higher than the frequency at which the wave is going, the wave isn't going to be able to propagate through. It'll be reflected. And so for low frequency, this is potentially an important mechanism that inhibits the transmission through the ISM or through the atmosphere. Right? So the Earth's ionosphere is a good example of this. And in general, the ionosphere prevents any extraterrestrial radiation below 1 megahertz from being observed at the surface. So if we wanted a telescope that could observe above, below 1 megahertz, we'd have to send it into space. And then there would be an associated frequency limit with the interplanetary medium, the solar wind, right? And then if we went outside of the solar wind, then it would be the ISM, and so forth. And so, the existence of this plasma frequency is interesting for us on Earth because we can actually use it to probe the electron density of the ionosphere, right? So we can send radio waves up and see where they're reflected, and there'll be a time delay. And measuring that time delay, right? So you send a pulse and you wait for it to come back at kilohertz frequencies. You'll see a delay, and you can measure that time delay and then estimate what's the ionization rate and what's the number density of electrons that exist at that range. And you can do this as a function of frequency to kind of probe various aspects of the atmosphere. Okay, everyone still with me? Any questions?
I have a question. So that means that the oscillation of the ions and electrons inside the medium are inside the plasma are like a property that doesn't depend on the wave. I mean, the oscillation is always there, and when the radiation try to pass through the medium, this oscillation, depending on the frequency, can reflect the radiation.
Yeah, basically.
Okay.
And I mean, the properties of that are just set up by the density of the medium. And let's see, so coming back here, we have, where's our definition of plasma frequency? Here. right? So these are constant, and so the only thing the plasma frequency depends on is the number density. And then you have obviously the frequency of the wave that comes through, but that's more or less it. So it's kind of set by that, but it has to be ionized, right? So it's the number density of free electrons.
Okay. Thank you.
Yep. Okay. So this is interesting. What is also interesting is even for frequencies above the plasma frequency, what that ends up meaning is that the medium is not a vacuum, right? It has an index of refraction, and therefore the waves will propagate at a velocity which is distinct from the speed of light. And so for frequencies above this, we can think about the electromagnetic radiation has a phase velocity, and the phase velocity is the frequency divided by the wave number, and that's proportional to c divided by n. And so this will actually, the phase velocity will be greater than c, and then we have a group velocity, and the group velocity will be n times c, which will be less than c, because n should be potentially larger than 1, but well, potentially could be larger than 1. It could also be less than. N here turns out to be the square root of the dielectric constant. And so it's just the square root of this quantity, right? And so for frequencies which are greater than this is going to be less than 1. And so this will be something that is less than 1 here. So you'll have an index of refraction which is potentially less than 1. Okay, and so then when you plug this in, you have a group velocity which is less than the speed of light. So we can think about the group velocity as just being this quantity, or you can sort of estimate it for frequencies which are very, very different from the plasma frequency. We can expand this, and we end up getting something which looks like this. So that's sort of fine. One kind of interesting aspect of this is that if we have some medium or the path along which the light ray is traveling, the electron density is not constant or uniform, then you're going to have variations in the plasma frequency, right, which will give variations in the index of refraction. And so you will have variations in the propagation speed for one. But what this ends up kind of a side effect of this is that the radiation will travel along curved paths, right? It's not a linear path anymore, but because you have an index of refraction, you have this potential change in the directionality of the light as well. And so from Schnell's law, right, we have that this wave number times n here. If we take it as a derivative of the path length, we have the sort of modification here of the index of refraction. And so what this means is that the intensity of light along a trajectory, it has a trajectory path length, L, and it has a direction, which is denoted as the unit vector K here. And what ends up happening is that the quantity intensity divided by this index of refraction squared is what's held constant along the ray, and not the intensity itself. And so, well, for a vacuum, okay, this is all fine, and the intensity is the intensity. But for the ISM, what this means is that you have potentially some minor deviations in the intensity between where it's emitted and where it's detected. And so we have to account for that in this index of refraction somehow. Another way that one application of this, which is particularly interesting, is that you have, let's say you have a pulsar, which is giving you, pulses of a certain frequency. So you have a pulse and then it stops and we wait, the pulse has a width of a few nanoseconds, and then we have to wait, let's say a millisecond or a second for the next pulse to come. And so the pulse, as it's traveling through, the pulse is a function of frequency, but you have all of the frequencies were emitted at the same time, right? But the propagation speed depends on the frequency now. And so as this pulse is moving through space, the higher frequency is moving faster than the lower frequency. And so you get a dispersion, a broadening of the pulse as a function of frequency, because the lower frequencies are moving more slowly than the higher frequencies. And so if you look at a pulsar and you can look at it as a function of wavelength, right? You measure the pulse, you see how offset low frequencies are from high frequencies. You can use that time delay to estimate the number of electrons along the line of sight. If you have some estimate of the number of electrons along the sight already, then you can estimate the distance, because it's the number, it's the electron density times the path length, which is important. And so we can think about, here's the delay, the dispersion delay. And so this is just the group velocity integrated over the line of, between ourselves and the object, minus the sort of theoretical time in a vacuum. And so you can, plug this in, you can plug in your phase velocity and your frequency dependence here, which goes like that. And so you end up with a time delay, which is related to this equality here. So you have this thing, which if you recall, this is the dispersion measure. You have the frequency dependence, and then you have some constants. And so we can rewrite this in terms of the dispersion measure as this time in seconds, so about 4,000 seconds, as a function of our dispersion measure in units of parsec per cubic centimeter, and in terms of 1 over frequency squared in megahertz. And so this is an example of a pulsar, right, where this is the initial pulse, and as a function of frequency, you can see this is now phase folded over the known phase. And so say if we pin this phase down at high frequencies, you can see that there's a phase delay in the pulse, which actually amounts to more than one period over about 100 megahertz in frequency, right? And so you see it wrap around again and come down again and then start to wrap around again. And so it gets faster, the wrapping around gets more and more, the delay gets stronger and stronger as you go down in frequency. And so this is actually really a nice way to measure distances to pulsars. So if we estimate that the galactic plane has a crude number density of electrons of ionized electrons here of say 0.03 cm squared, then we can use this delay and as a function of frequency to measure the distance. And so, typically this will provide distances to about 30%, which is not terribly bad, right? And so typically, pulsar observations almost always cover a wide bandwidth. One of the issues here is that you need to, of course, correct for the differential delays when you do pulse searches, right? So if you're observing, trying to find new pulsars, what you do is you observe and then you will fold the data on a bunch of different frequencies and see, do a Fourier transform of it and see if you can see a peak. And if you don't account for the dispersion delays here as a function of frequency, right, which you don't know the distance beforehand. So you have to input a bunch of different distances and then refold the data and then see if you see the peak. And so it's that combination of having to fold on various frequencies and fold on various distances, which makes it very computationally intensive to do this. So you have to basically have this extra dimension for the search. Another interesting thing that can be done with pulsars, of course, is that you may have a situation where you have a pulsar and there might be an intervening H1 cloud in between us and the observer. And so, of course, pulsars are bright. And so you could potentially measure H1 in absorption along the continuum of the pulsar, which might look like this. And so you can compare the H1 from the pulsar that's in absorption versus the total H1 in intensity, the emission line along the line of sight. And you can kind of use that to get another estimate of the distance. And so you can compare these things, and then that allows you, this extra estimate of the distance then allows you to estimate what the average electron density is along that line of sight, right? So you can play this game where you use one technique to kind of refine the other one, or to build a model of the galaxy. Okay, the other component here, right? So we mentioned that the light is going to travel along curved paths, and that if the electron density varies, the index of refraction varies. And so you can imagine that in an inhomogeneous medium, right, you're going to have slight deviations in the path. And so as the waves are propagating out radially, what happens is that this extra sort of dispersion, or this extra curvature in the paths, will tend to widen the paths of the light. And so this is known as scintillation. And so the variations in the refractive index here will mean that you have some distortions here, and you have a coherent radiation that's coming out in, let's say, a plane wave, and it will end up being sort of modulated or disturbed, right? So the wavefronts are ending up being disturbed, and so you end up with a diffraction pattern at Earth, which is not clean. And so this tends to be problematic in terms of, this is a source of noise for, say, coherent processes, coherent radiation coming through. And then the other thing, of course, is that this tends to broaden the angular size of the source. So the intensity will vary as a function of frequency, and the size of the source will vary as a function of frequency. And so the power spectrum of this sort of thing, will be dependent on the angular size of the source. And so typically, the dominant component here is the interplanetary scintillation. So it's the solar wind that we have, that we're sort of embedded in. And of course, this varies depending on whether we observe outside, towards the outer portion of the solar system, or towards the inner portion of the solar system, right? So it depends on the time of year that you might observe an object, and so forth. So it can be a little bit complex to think about. But one of the interesting aspects of this is you can actually use scintillation to place constraints on the size of compact sources, because, right, the incoming wave should come in sort of all perpendicular, or in a plane, and depending on the size of the source, you may have some variations here. And so if you have a very, very compact source, the fact that it doesn't scintillate, or it only scintillates at a certain frequency, allows you to put a limit on the size of the source, which is kind of cool. So that basically you have the outgoing waves go like this from some source which is not a point source, and then you can measure the distortions in the waves, and those distortions will have a sort of certain pattern in Fourier space that can allow you to place constraints on the size. So this is just an example of the broadening effect from scintillation. So at high frequencies, you have a fairly narrow peak, and as you go down in frequencies, you start to see a strong broadening. Now, obviously, this is pulse phase, right? This is phase wrapped, and so the phase will always be towards delaying something, and so you end up with the broadening only going in this direction, because, right, you're slowing things down, but you also have this major broadening. And you can see it's very noisy, right? It starts to get much noisier. It's hard to observe. This is what's known as a diffractive scintillation sort of analysis. And so this is the time here and then the frequency. And you can see sort of modulations in the intensity, which are happening because of the scintillation effects. And so if you take a Fourier transform of this, right, this is from 2 different days, and you can see the different patterns here, which are printed on this from, partly from the atmosphere, and then partly from the fact that the Earth's moved a little bit, and so forth. And so these are Fourier transforms, sort of called secondary spectra, and we can see that most of the patterns in these images tend to reside along these arcs, which are known as scintillation arcs or moving arclets. And so, by measuring the sort of pattern of this, you can gauge exactly what's going on here. Right? And sometimes you have deviations from this. And so this allows you to say something about the medium and about the compactness of the source. Okay, any questions about scintillation and broadening? No, okay. So we can now go back and add magnetic fields. And now if we consider that there's an external magnetic field in the interstellar medium, that makes the plasma anisotropic, right? Because the field has some direction. Initially, we can assume that the field is uniform and measure everything for a sort of uniform field with plasma effects. And so what this ends up meaning is, because you have a directionality to the magnetic field, there are going to be different, the plasma properties will vary as a function of whether the field is perpendicular to or parallel, the incoming wave is perpendicular or parallel to the magnetic field, right? And so the wave properties and the propagation is going to be different depending on the relative angle of the wave with respect to the magnetic field. And of course, we can also expect that there'll be a cyclotron frequency, which will kind of go as this relation here. Right, and this will enter for non-relativistic plasmas, which are the most typical ones. And so typically what is done here is that we ignore the particle pressure, and this simplifies things quite a bit. And this is known as the cold plasma approximation. So let's implement that for the moment. And we now want to calculate what the dielectric constant is. And the dielectric constant is now going to be a tensor. And the waves are, will have different polarizations. And so we want to think about this as this coefficient E field will multiply this, the wave coming through. This thing is not going to be a constant anymore. And so if we assume that the fixed magnetic field is stronger than the fields, and so it's sort of the dominant effect here, then the wave, the equation of motion for the wave in these, in the Coulomb field and the magnetic field becomes this, right? So we have our acceleration is equal to the Coulomb field part and our magnetic field part. And so if we imagine that we initially have a wave coming in or light coming, which is circularly polarized, meaning that it's a sinusoidal wave, the time dependence of the electric field is going as this, right? So equal components in one unit vector versus the other, but they vary with time, right? And so we want to see how the waves propagate in a uniform magnetic field. And so we'll take the magnetic field to be in the B direction, the Z direction. So it's perpendicular to both of these for simplicity, to get the sort of maximum effect. And then we can imagine that the time derivative here, if we have something of the form of this, that's going to give us, this time derivative is just going to give us a complex I here and the frequency. And so we can think about the frequency, we can move mass over here, and we can think about this as this velocity will be proportional to the charge and this extra component here now, which is we now have the frequency and our cyclotron frequency. And then we have our propagating E field. So this is how the velocity is going to vary with time. And our revised dielectric constant then is going to look like this. So it's 1 minus the plasma frequency squared. And instead of just our frequency squared, we have frequency times this plus or minus cyclotron frequency. And the plus or minus corresponds to whether we have right-handed or left-handed polarization. And so obviously, right-handed and left-handed polarization are going to have different dielectric constants, right? If this is some value, this is going to be, something, or this would be W plus WB or W minus WB. And so we now have different propagation speeds for the different polarization length. Right, that's ultimately what this means, because this dielectric constant is related to our index of refraction, right? And so we also have the potential of having different deflections for different polarizations, which is also problematic. So if we imagine that we have some plane of which we have a linear polarized wave. This linear polarized wave is effectively the superposition of two circularly polarized waves, right? We can always rewrite that in terms of circular polarization. And what's going to happen is that over time, as the wave propagates, the different polarization handedness are going to propagate at different speeds. And so what's going to happen is that the linear polarization is going to rotate, right? And this is known as Faraday rotation. And so if we have a constant wave number here, we can think about a phase angle of rotation of the electric vector as being k times d, or k dot product with d, where d is the distance across which this thing travels. And so this is going to be equal to 2 pi d divided by lambda, where lambda is the wavelength of the light. And so more generally, we can compute a space varying wave number. And so we have our sort of handedness here, which is going to be, this is the sort of overall change in our wave number across our distance here, right? Whether it's right or left-handedness. And so our wave number is going to be related to our dielectric constant in this sort of proportion. So it's just the frequency divided by c, which is sort of normal, but we have this extra component. And so the wave propagations are going to change, right? Or be dependent on this handedness. And so we have a plane polarized wave. It's going to get rotated by an angle, right? A linearly polarized wave will be rotated by an angle delta theta, which is going to be proportional to the difference between these two propagations, or the half of that. And so if we assume that the frequency is much higher than the plasma frequency and the frequency is much higher than the cyclotron frequency, then this propagation can be expanded to look like this, right? So if we have a Taylor expansion, it ends up looking like this. And so we can more or less calculate that. So this thing here, right, it's equal to this minus this over this distance, and times 1/2. And so we can plug in our value, we can plug in our value for right-handed or left-handed. And so we end up with this difference here is going to be proportional to this, right? So it's proportional mostly to our cyclotron frequency, the plasma frequency squared, 1 over the frequency squared, and then our distance. And so this thing, if we plug in our knowledge of the cyclotron frequency, that's dependent on the perpendicular magnetic field, right? So going back here, right, it's proportional to this. And then we had our plasma frequency, which was proportional to the number density, right, which is here. And so we need to integrate these two things over the distance, and then everything else pops out of this integral. And so this thing here is a function of the wavelength squared and the ionization, the number density of electrons along the line of sight and the perpendicular magnetic field component. It's the combination of the two. So typically if you just measure Faraday rotation, there's degeneracy between these two, right? And the distance. If you knew the distance, you still wouldn't be able to pull out the magnetic field unless you had some estimate of the electron density. Now, the benefit, of course, is that you could also measure the electron density from the dispersion measure. All right, so you could measure the variation as a function of frequency of these parameters, and that would give you the average column density of, or the actual the actual density of electrons. And from this one, you have the average electron density times the magnetic field. And so if you take the ratio of those two things, you'll get the average magnetic field along the line of sight. So if we measure the relative rotation at different frequencies, based on this, what that tells us is the effect of the magnetic field, right? And so this plus this would equal this sort of rotation, or rather there's no rotation, but this, and then you will move it, right? So this is what it was emitted originally. This is what we get later on, if relative to this, if this doesn't change, we have a motion of the right versus left-handedness, which changes as a function of distance. And so you get a linear polarization, which is offset, right, or rotated from the original. So typically, one of the other aspects, of course, of this is that this magnetic field can vary. It doesn't necessarily have to be constant over kiloparsecs, right? And so it could have small scale variations, possibly by quite a lot. And so the Faraday rotation measurement is generally a lower limit on the actual amplitude, because if you have variations, right, they'll tend to cancel out or to rotate back and forth. And so that's lost in the ultimate measurement that we make, right? Because we're making the cumulative rotation measure here. Okay. So combining the pulsar dispersion and the Faraday rotation, we can get an estimate of the mean magnetic field along the line of sight, or a lower limit on it. And so you could imagine, let's have an example here where we have a pulsar and it has a time delay signal of t as a function of frequency, which goes as 10 to the minus 5. And we have Faraday rotation, which implies that the change in angle as a function of frequency is going to be about 2 times 10 to the minus 4. And so if we make the measurements around 1 megahertz, we don't know the distance to the pulsar yet. But it turns out those things will end up canceling in the average. And so generally we will have an average magnetic field, which is the integral of this divided by the integral of this, which is what I said previously. And the ratio of this thing here to this thing here, right, which are actually measured quantities that don't depend on the distance, this ratio to this ratio will end up giving us a constraint on the magnetic field where the distance drops out. And so we measured this, and based on this sort of equality or approximation here, we would end up getting an estimate for the perpendicular magnetic field about 10 to the minus 6 Gauss, right? So a microgauss, which is a very typical value for the ISM. And this value would generally be independent of frequency, right? So if you made this measurement at multiple frequencies, because, well, this is a change in frequency, but you could, say, okay, we see the change in a small portion of frequency here, and then here, it should be roughly the same. And so you can gauge the magnetic field by that. Okay, any questions on this? On Faraday rotation?
We can see the effect in the atmosphere, in the Earth atmosphere.
In general, yes. Although
polar lights, maybe?
Yeah, I mean, I think it depends on the frequency. It ends up being, I think, relatively small effect. I suspect that because we were assuming the B field is stronger, sort of dominates here, then we end up seeing this effect. And I think in the atmosphere that may not be true. Typically you don't have to make a strong correction for the atmosphere, but you do have to make a strong correction for distance, ISM. So I think the dominant component for rotation measure is the sort of large scale path. But yeah, I guess it would be a fun problem to calculate.
Thank you.
Okay. But yeah, I don't know the answer of him. Okay, any other questions? No. Okay. So the final sort of subset of topics here is related to the propagation speed. And so we had talked about n being higher than 1. And so we can kind of think about this the other way around. And so what happens if, all the radiation from all the processes that we discussed, it's going to be subject to the influence of the plasma. And what's going to happen is we've already discussed that, very little radiation will propagate below the plasma frequency. And so if you have a pulse of radiation, the pulse dispersion and the path curvature will occur for frequencies above the plasma frequency. And Faraday rotation or Faraday polarization will also set up what will effectively be a polarization screen, right? So it'll any Faraday rotation that happens will generally tend to depolarize a strong polarization signal. Now, there are other effects here which actually fundamentally modify the radiation process itself. And so we can think about the induced motions and the emission of particles which occur in an ambient medium responding to the radiation. And so this is sort of a lot to think about. So let's give you a couple of examples here. So if we consider a macroscopic dielectric constant of a plasma, and let's say that it's independent of frequency for the moment. Now, this isn't really true, but just makes things a little bit easier to calculate. So basically what we want to do is capture the basic idea here of a collective response of the medium to a process. And so in the presence of a dielectric, this constant dielectric, Maxwell's equations look like this, right? And so we can rewrite Maxwell's equations substituting the E field goes as this, the B field goes that, let's see, I forget what this is, the potential, this is charge potential, this is current potential, there we go. And so the current potential goes, has a modification here, and then the charge goes like this, the speed goes like this. So what these mean is if we go back and we resolve the Leonard-Reichert potential, then this current potential has this extra factor of the dielectric constant here and here. And so this thing here, right, which was kind of our relativistic component, or the thing that kind of drove much of the radiation that we saw. This thing now has a dielectric constant component in it, and the current potential doesn't is still more or less intact. And so what this means is that we have a propagating E field which goes like this, and we have this extra component here, and we have this thing cubed down here, and then the B field is compared to the E field as follows. So there's again this extra component, and so this is going to modify the radiation that comes out, right? And it's also going to modify what happens to the speeds of the radiation that comes out. And so one example of this is Cherenkov radiation. And so we can think of, let's have a charge moving through, it moves uniformly through a vacuum and it doesn't radiate, right? There's no acceleration there, there's no force, there's no energy change. And so it's all consistent. Now, if we have a charge moving through a non-vacuum material, so a dielectric medium, this same thing holds. There'll be no acceleration, no force, no energy change, as long as the particle velocity is less than the phase velocity of light in that medium. Right. So basically, it comes back to one of the components of this dielectric constant. And so, what this means is that the Leinart-Werkhardt potentials are not changed really dramatically, right? They still propagate as 1 over r squared, but there's an extra sort of factor in here. And so for certain frequencies of radiation, for instance, or certain densities of material, things will be modified. And so if we imagine that the medium has an index of refraction larger than 1, what this means is that the particle speed can now be larger than the phase velocity. And so this thing, right, so this is greater than 1 now. And so this now can vanish when the cosine is equal to this, right? Where n here is now the square root of the dielectric constant. And so what this means is the potential can become very large at places where this still holds. And basically you can have effective radiation with the 1 over r term still. But this is not necessarily going to be 0 at large distances, as the case was originally. And so the particle can sort of radiate because we have a modified version of this. Okay, so what does this mean? So let's say we have a velocity which is greater than the speed of light divided by our index of refraction. And so now, if we think about this case, so right, this thing is propagating, and this is the case when the velocity is less than c divided by n. So we have, right, we have something going and it's propagating out, and then we move here and it propagates out. Actually, wait, sorry. So 1 is here and it takes some time to propagate out. Then you move to 2, it propagates out, 3 propagates out, 4 propagates out. And you always have one potential, which is not intersecting with anything else, right? If the velocity is greater than this, what happens is that this is propagating out and this moves, and now this is propagating out, and this is propagating out, and this is propagating out. And so there are points here where you feel the potential from the charge at 2 different places in time. And so what happens is this forms a plane where you're intersecting 2 different points or multiple points in time. And so the potential is altered in a way, right? Because of this index of refraction. And so this will then sort of create a special effect. So what happens is we basically have 2 different regions here, which this cone, which is denoted by the dashed lines, is called the Cherenkov cone. And so outside of this cone, there's no potential yet, right? It hasn't propagated out. Inside of the cone, we have the cone is intersected by 2 spheres at all times, or even possibly more. And so it feels the potential from at least 2 positions of the particle. And so the radiation that comes out from this combination, right? So initially, this propagation out was considered the light that was coming off of this. But now we have the fact that we have it's combining And so the light, the propagation, the components of the light that come out are now being modified by this multiple potentials intersection. So we have this outward sort of motion. So as a function of time, right, as this moves out, this cone will propagate this way, and we'll have something like this. So this is moving out in this direction and this direction over time. And so this pattern is kind of similar to an airplane, supersonic airplane. And so you have a shock pattern that goes from behind, and it kind of follows the plane motion. And so the relation here, right, if we have, this is some angle, this is the velocity with which this thing is moving, and so this is the distance, v times t, and so this is the propagation, which is going to go at c divided by nr times t, and so it'll go out at this direction. And this relation will be dictated by this equality here. So the cosine theta is equal to the speed divided by the speed of light times our index of refraction, 1 over that. And so for cosine less than 1, this holds. And so it follows that the velocity should be in the range between c and c divided by nr. And so the precise direction of this radiation coming out ends up giving you a measurement of the speed of the particle. Right, so this is propagating out, and this plane here is related to this speed. And so high energy particles, which are moving through the Earth's atmosphere, right, which has a dielectric constant, it's not a vacuum, they will slow down, as they're interacting with this medium, they will emit light, and that light will be cast off in this sort of plane moving at some angle with respect to the path of motion. So if you set telescopes here and you set them here, and you measure this, you can locate it on the sky, and then following that as a function of time, you can figure out what the particle velocities were, and you can plug that back in and estimate what the cosmic rays were doing, where they were coming from some direction, and their speed. Okay, so this is a very interesting way of detecting high energy particles that enter the Earth's atmosphere, and the radiation can be very intense, and it acts as an effective mechanism for energy loss. The main effect here is mostly operating on weakly ionized plasmas only. When you have a very highly ionized plasma, then the conductivity is large, and the conductivity then ends up dominating the index of refraction. And so you have to modify your estimates here. And so this was all under the assumption of this Cole's plasma approximation. But if you really wanted to be careful, you'd have to actually use a fully ionized plasma and deal with that, right? Okay. Another related effect. So this was when this index of refraction was greater than 1. And so we also have the case where the index of refraction is less than 1. And so again, we'll talk about a cold plasma here. And if the index of refraction is less than 1, there's no Cherenkov radiation. And in this case, what happens is that the beaming effect of things like synchrotron radiation are dampened, right? They become less potent. And so we can, again, think about this. So if we have the beaming is going to be related to this K factor again, right, which is related to this. And so for n less than 1, what happens is that this beaming effect is going to be suppressed, because even if you have velocity close to the speed of light and you have a cosine close to 0, it's still not going to be 1. It's still not going to be 1 minus 1. Right? It'll be 1 minus something less than 1. And so the beaming is diluted. And so no matter how large you make this, right, this thing can still be significantly larger than 0. And so if we imagine the original beaming in a vacuum looked like this, the angle of the beaming went as 1 over gamma, and that one is as 1 minus beta squared, square root of that quantity. For a plasma, what happens is we have this extra factor here of the index of refraction squared. And so this is not 1, right? So this is diminished by some value. And so the angle is going to be wider. And we can think of this as this angle here. If we had beta equals 1, then this angle is just dependent on the index of refraction. And the index of this thing, we can rewrite this. We can plug in what we had for the index of refraction, which was the dielectric constant, and we can plug in it's the plasma frequency divided by the frequency. And so this angle is going to be dependent on the frequency with respect to whatever the plasma frequency is, which is dependent on the number density of electrons, at least for a cold plasma. And so at low frequencies, what this means, if this frequency is lower than this thing, then what happens is that this thing never gets very, very beamed. And so you never have the components that can make up something like synchrotron radiation, which is entirely made because you get a beaming effect going on, right? So you get something which is beamed and kind of enhancing things. And if you have a frequency below the plasma frequency, you can never generate that. The beaming never happens. So at high frequencies, this thing will decrease until it gets to 1 over theta, or sorry, 1 over gamma, right? And so if you are at high enough frequency, then this thing reverts back to its normal sort of behavior. But for frequencies, this is really only for frequencies much higher than the plasma frequency. Below the plasma frequency, what happens is that you start to choke off the synchrotron. And so below a frequency which is gamma times the plasma frequency, the spectrum will be cut off. And so the plasma frequency, we just calculated it, right? It can be sort of order kilohertz. And so if you have gamma of 10 to the 3, then you're talking about the spectrum being cut off at megahertz values, right? And all it means is just that you have a synchrotron and it gets up, the frequencies get close to the plasma frequency and you have an exponential cutoff. And so this effect will typically dominate around, all frequencies below this value will be cut off. And so this is because if you have a large gamma, this can be pretty high. And so this might be the dominant effect for low frequencies. And another way of thinking about this is the following. So you have the electron is moving around, right, in helical motion in the magnetic field. And the electron, it's that motion is leading to this beaming every time it's in our direction. And so if you sort of widen that, then what happens is the propagation speed is slowing down. And so it never has a time to catch up and reinforce the synchrotron emission the way that it kind of looked like a cone in space before. And so this ends up choking off the synchrotron as a function of frequency. So the enhancement basically is the same as the Cherenkov one, but in the case of Cherenkov radiation, the particle actually catches up and completely overtakes the potential, right? Whereas this is not being able to overtake the potential. And so this is known as the Raison effect. And it's a relative effect in the sense that, it depends on the particle speed approaching this thing. So it depends on gamma and it depends on the density of electrons. And just to give you an idea, so here's optically thin synchrotron emission, and you actually can see a variety of different cutoffs. And so the synchrotron self-absorption looks like this. It has a component spectral index, which goes as 2.5, or rather minus 2.5. And then you have the exponential cutoff from the raising effect. And so depending on the density of the medium, and these are potentially subtle. So if you don't have a lot of measurements, you could assume that this is synchrotron self-absorption, and really it's an exponential cutoff. So which has to be a little bit careful. Okay, so that's all I wanted to say about plasma effects. There's a lot of different ones, and they come up in different scenarios, but they actually can be very useful to measure the number density of electrons in plasmas along the line of sight, and also to potentially measure the magnetic fields and the distances. Any questions? No? Okay. And I guess I will see you guys on Wednesday. Yeah? Okay. Ciao, everyone.
Bye-bye.
Bye-bye. Thank you.